Hello everyone, and welcome to the last week of the differential equations class. This is not a tested material, but rather a course revision. But I think some parts of today's lecture, especially this part about further investigation in nonlinear systems, are going to be relevant to your project work. But anyway, so what I want to begin with is a topic that is a bit hard to test, but I find it very beautiful and very nicely laid down in the whole course, and also linked to linear algebra, so I am going to present it. Yeah, and also it relates to real analysis and other kind of stuff. So recall that an exponential function can be represented as the sum of its own Maclaurin series. So this series converges for all real values of t. The radius of convergence is infinity. But if you think about it, then it makes sense for matrices too, right? So if you have a matrix, you can just calculate a square, a cube, and so on, and then you put it up together, and then you get an infinite series. So, which is going to be a matrix. All right? Then, now, suppose that I want to do this. I want to take this f of t, which is the exponential function of the matrix t times a. So a is a matrix, t is a number, t times a is still a matrix, and then I can take the exponential function, and then if you try to differentiate it, just like according to the common sense, then you will notice that the derivative satisfies this matrix differential equation. F prime of t equals a times f of t. So, but then if you think about it a little bit further, and let me maybe mention that A here is an n by n matrix. So TA is again an n by n matrix. So exp of TA is again an n by n matrix. So f of t is in turn is an n by n matrix. And this is a matrix equation. But it all makes sense. So n by n matrix equals n by n matrix times another n by n matrix. Well, but columns of the right hand side, they just found by multiplying the matrix A, rows of A with columns of f of t. So in other words, what we essentially have is that if x is any column of the matrix x of ta, then its derivative, because it depends on t, so we can differentiate it entry by entry, then its derivative equals a times x. So in other words, we constructed a solution of the system of linear differential equations. Wow. That is very impressive. But of course, there are some issues with this approach. The first issue is that by definition, exp of ta is the sum of the infinite power series. But how can we prove that it converges for all values of t? And furthermore, how can we prove that it is a rigorous mathematical operation, that if we differentiate it term by term, then again we get a new power series that converges for all values of t, and the sum of the new power series is what we expect it to be, so the derivative of the original power series. And another issue is that whether or not we can actually compute this exponential function of the matrix. Yeah, the first question belongs to real analysis, and I think you should talk to your real analysis lecturer. But the answer is yes, so it is provable, and it is not even very hard. And the second question is actually related to linear algebra, but I would like to explore it a little bit further, because we've been building up some links to linear algebra throughout the whole course, so why don't we look at this one too. So let's begin with an n by n matrix X. And then if we want to calculate this matrix X with respect to a different basis, then it means that we take the conjugate, multiply n times again. Long story short, the important thing is that the exponential function, since it is defined by the power series, when we take the exponential function of c times x times c inverse, c and c inverse can be factored out on the beginning and on the end, and then we can just get this. So why is this important? Is because if the matrix X is diagonalizable, then it means that X can be expressed as C times A times some diagonal matrix times C inverse, and then a diagonal matrix is it kind of nicely suits to calculate the exponential function of. So, which means that in case when D is a diagonal matrix and X is a matrix conjugate to a diagonal, then here is the answer. Now, how can we put it? How can we apply it to the theory of differential equations? And here is an example. Of course, you know how to solve this system. We've learned how to do it in week 10, I think. So we need to find eigenvalues and eigenvectors. And then we see that our matrix is indeed conjugate to a diagonal matrix. But then, by applying the equations that we've just learned, we can calculate this thing in the middle. And then we can multiply by these two matrices. This is C, this is C inverse. And then we get the answer. And so the final answer is a linear combination of the two columns of this matrix. All right. Of course, the final answer is the same as the final answer of the method that we learned in week 10. So, what is the essential advantage? Well, besides the beautiful theory, the advantage of the solution of the ODE system in terms of the matrix exponential function is in the fact that not only it solves the system of equations, but also it solves the initial value problem. This is because, you know, if you just look at this, and if you let t be 0, then x of 0 equals e to the 0 is going to be 1, x of 0 is c, so c is x of 0. Therefore, we have already a very compact and very beautiful formula for the solution of the initial value problem. All right, I hope it justifies the theory of matrix exponential functions. Well, just I would like to mention a few more little things. That essentially we have got these two results, that we have a general solution and the solution of the initial value problem. These two theorems or two results are true, regardless of whether the matrix A is diagonalizable or not diagonalizable. So diagonalizing A is just a practical means to actually compute the exponential matrix function. But even if the matrix is not diagonalizable, it is always still possible to compute the exponential function by the means of the so-called Jordan canonical form that I don't think you've learned in linear algebra, but at least those of you who took the advanced investigations, you probably know it. Even if you didn't, you can always Google it up. It is a bit harder than diagonalization, but it is not really rocket science. So if you're interested, I suggest that you try to figure it out. But here is how it looks like. So basically, the Jordan canonical form looks like when you have eigenvalues on the diagonal and ones right above the diagonal and zeros at all other places. And then if you put your matrix into the Jordan canonical form, then you can still compute the exponential function of the matrix. For example, the reason is because what you need is a simple closed form for powers of the matrix, and if your matrix is in the Jordan canonical form, it is still doable. And this is basically how, say, MATLAB does it. In MATLAB, you can write exp of matrix, and then it will compute it. Okay, so let me summarize. The solution of the initial value problem of a system of differential equations can be given by a very short and nice formula that involves the matrix exponential function. Then computing this exp of TA is also about eigenvalues and eigenvectors. So the beauty of the matrix exponential function is that it gives a nice and simple solution of the initial value problem. Well, and then in order to actually compute exp of TA,